Okay, I have a little different setup in my office today. I've plugged in one of my monitors with my laptop. My laptop tends to have better sound recording, I found. Plus, I can write on the screen with my fancy Surface Pen. But then I have your pictures of you up here on my other monitor. So if it looks like I'm looking up, that's because I'm looking at your pictures. The actual slides are going to be down here on my laptop. So tried to get it as best as I could. So yay, welcome back. So we finished chapters, what, 5, 6, 7, and 8 last time, and the test for 5, 6, 7, and 8 is up, and you have till tomorrow at midnight to take the test and turn in the homework for those 4 chapters. So I want to give an opportunity to start out class with asking questions about the homework. The one thing I want to, let's see if I can get my mouse. It's up and down, and I got a mouse over. There we go. Let me, let's see. Share my screen for just a moment. I wanted to show you guys. Okay, can you see my screen now?
Huh?
So no, it's on 8 and homework 8. 7. We were just there. 7, homework 7. Item 7B6. There was a typo, a small typo on my part. So this is 7B6. It's a psychologist who's looking at the enzyme in saliva and chronic anxiety levels. Down here on the answers, the second answer box for you to fill out is for the pool standard deviation. I had put SP with a little p, but that should have been SP squared. So if you're working on this homework, you might want to refresh your screen, and that change has been made now. You notice the formula in the yellow box, it's SP squared, and we leave it as SP squared because that's what goes into the standard error formula. So it was my typo down here in this little, by the answer box, it didn't have the square on it, and that was on me. But that's been fixed now, but I wanted to make sure everyone knew about that. Okay, so that's the one thing I wanted to say. I will stop sharing my screen now. How do I go with that? And then let you guys ask questions and share your screen.
I just have a quick question on if you can just help me remember on the Shapiro Wilkes test and the Levine's test, if you, what it means when your p-value is greater than 5%. So what is the null hypothesis for both of those tests?
Great questions. So I will go back to share my screen again. Actually, no, I don't want to share screen. I want to share a whiteboard. This is cool. I can share a whiteboard. Okay. Guys, can you see my white? It's just white now, or would it be sharing my screen? Okay, actually, I need to move this one over to this screen because this is the screen I can write on. Okay, so we have learned 2 preparatory tests, and they are Shapiro Wilkes test and the Levine's test. These are both for testing assumptions. Oh, it used to be, I could use, how do I, supposed to, yeah, no, there's scribbles.
Hey, Dr. Schwartz, if you're writing, I can't see anything on.
You cannot see the writing?
No.
No.
You guys can't see, oh my gosh. Okay, let's try this one more time. It's not gonna be good if you can't see the writing. Okay, share whiteboard, share. Can you see it now? Give me a thumbs down if you can't see it. Okay, I want to see everyone. I can't see everyone's faces yet. There we go. Not Kelly, you can't see it? No. Anyone else not able to see it? Okay, Kelly, on your Zoom, if you're using Zoom, is there a second window? Sometimes there's another icon that you can click on to see someone's shared screen. Are you seeing all of our pictures?
Yeah, I can see all your guys' pictures here to the side.
But you're not seeing the white, it's a white screen?
I can see a white screen, yeah.
Can you see a little bit of green writing, like scribble handwriting? Nothing. Can you see that green X? Okay, so I'm going to erase.
Oh, I got it. I changed my view options to fit to window. So
Oh, okay. Good, 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 good. Okay, so now everyone can see. Okay. I'm gonna drop there. So we've got the Shapiro, Wilkes, and the Levines. Okay, so for Shapiro Wilkes, why do we use Shapiro Wilkes? What was the purpose of Shapiro Wilkes? Can somebody remember?
That's to test normality.
This is to test normality. And the null hypothesis is nothing going on. So that means there's no violations of normality. So this is that your variable that you're testing, see that eraser won't, is, come on, drop, is normal. So this is the purpose. So if your p-value is, say, like 0.002, that's a tiny number, that means that you have violations of normality. We violate the assumption of normality, which is a requirement of the t-test. If your p-value is something big like 0.357, then that means that there are no violations. So that means that you, it's okay to do your test, your t-test. All of the t-tests, the 1 sample, the 2 sample with the pooled variance and the 2 sample with separate variance, all of those t-tests, all of them require normality. Every single one of them. So this is a test you have to do. Test your continuous variable, dependent variable to see if it's normal. Now, usually what's the best way to test normality? Even better than Shapiro Wilkes is to make a histogram plot. That's the best, or a QQ plot. That's the best way. But this is like the official p-value test for normality. This test is super, super oversensitive for a big sample, and it's not sensitive enough for a small sample. And that's why I'm not a huge fan of it, but people do use it. Sometimes we have to use our judgment. So if we have a sample size 5 or 6, this is always going to have a big p-value. We have a very small sample, it's never going to be able to say that it's not normally distributed. And a histogram is going to be really hard to tell if it's normally distributed with just a few data points. And so you have to go off judgment. The thing that I'm measuring, is it realistic that it's normally distributed in the population? So if I'm looking at a variable like number of children in a home in Cache Valley, do you think that's normally distributed? Or do you think it's skewed? There's going to be lots of 0s, 1s, 2s, 3s, and then it's going to taper off to 4, and we're going to have this tail going to higher numbers. So sometimes you have to think about the variable you're measuring and think in the population, is it realistic that it's normal-ish? And so even though we have data, if we have a small size to our sample, nothing's going to be really good at assessing normality. It's a judgment call. And a lot of times at this point in statistics, you guys, grad students, statistics becomes less of a science and more of an art. There's more subjective decisions that you have to make. And grad students hate that because they want to have a recipe. But it's just a fact that sometimes we have to make a subjective judgment call. And sometimes there's not super, super hardcore evidence one way or another. We have to choose, and we have to do the best we can to back up our choice. And so I think it's very important in those cases that you're clear about what choice you're making and why. And sometimes people are going to argue against you, but as long as you say what your choice is and why you're going with it, you're going to be able to stand up. But you're always going to have to defend those choices. The worst thing is to not say that you had to make a choice and pretend, bury your head in the sand and say, this is just the way it is. Okay, so
See,
that's
Sarah, doesn't Levine's do the same thing as Shapiro Wilkes?
not the same thing. Shapiro Wilkes is looking at normality. Levine's test is looking at, does anyone remember?
It looks at they're different.
It's comparing groups to see if they
Oh,
have not the same shape of the distribution, but the same
standard
spread.
deviation.
So this is looking at, this is a test for homogeny of variance. And the null hypothesis here is nothing's going on. If nothing's going on, that means that the spreads are the same. So this is, the null hypothesis is that the groups have the same spread. Or same-ish, you know, it's like not normal to a perfectness, but normal-ish. They're not going to have the exact same standard deviation, but they're going to be close enough we can treat them as if they're the same. So for Levine's test, if you get a p-value that's super, super tiny, that tells you what? Reject the null hypothesis of nothing going on. Something's going on, and the something is that they have different spreads. This is that the groups have different, I'm running off the page here, spreads. Now, this is not a deal breaker for the two-sample t-test, but it changes what you're going to do. No, I need to get the eraser. I'm gonna erase some of this here. We have enough room here. Let's change to a different color. Let's go to purple. So if your p-value is really little, then that says you violate HOV, meaning the groups have different spread. And this is where you have to do Welch's degrees of freedom and the separate variance version of the t-test, two-sample t-test. If your p-value comes out to be something bigger, and what's our cutoff there between small and big? About alpha 0.05, that's going to be our cutoff. If we have a big p-value, that means we cannot reject the null hypothesis of nothing going on, same spread. So when that p-value is bigger than whatever our alpha is, that means that we're HOV, homogeny of variance, is supported. And we can do the pooled variance. I can't write down there. Pooled variance version of the t-test. The two-sample t-test. We should be doing Shapiro Wilkes for both one sample and two sample t-test. The one sample, go bigger. And the two sample. You'll notice in the homework, it didn't actually ask you to do it for the two sample. Lazy. Levine's test, we do not do this for one sample, because it's saying do the groups have the same spread? And if we only have one sample, we only have one group, so there's no other group to compare it to. We only do Levine's test if we have two samples.
Can you remind me if for Shapiro Wilkes test, since we're doing it for one sample or two sample, and you could have a violation because you said like this, the note said that you can have the central limit theorem kick in and it's okay for large samples. So for one sample and two sample, are we talking about 100 for one, but for two sample, are you saying 50-50 or 100 together? Or what's kind of like our rule of thumb?
Rule of thumb, yeah.
If that isn't normal, that's okay because we have the central limit theorem.
So the central limit theorem is where it says even if our samples and population are not normally distributed, the mean of the sample will be normally distributed. Central limit theorem. That takes over for the normality assumption, and the sample size you need usually is 30, not even up to 100. If you have sample size 30, now, yeah, you're right that we only talked about the Shapiro Wilkes normality assumption in terms of one sample. We didn't really set a rule of thumb for two sample. That 30 being a big enough sample should apply to both groups. Both groups should be big. But here's the thing. If your population is normal, the means are guaranteed to be more normal. And how big of a sample you need, I said 30 here, but that's depends on how not normal the sample is. If the population is slightly skewed, the central limit theorem can take over with sample sizes of as small as 10. If the population is wildly skewed or trimodal and really wonky, then you would need up to 30. So that's why it's hard to give a solid, always big enough sample that you need. This is kind of the crafty, artsy part of the stats. And because of that, most distributions are not perfectly normal, but they're normal-ish enough that even sample sizes of 10 and 15 are okay. And most of the time for the effect sizes we look at to have enough power, you're usually going to have sample sizes of over 12, or you're very rarely going to actually do a 2-sample t-test with groups of 5 and 5. It's really not big enough to have enough power to detect an effect that you would realistically be studying. Tiny samples just don't have enough power for most things. So because we usually have sample sizes of at least 12 or 20-ish, it almost always is the case that the central limit theorem takes over for the normality in the population. And that's why Shapiro Wilkes, even though it's technically should be ran for a 2-sample test, we sometimes get lazy and don't actually run it. Those are really good questions. as soon as you get your data from any study, you gather data, the first thing you should do is plot your variables. Plot to understand the distribution one at a time and to investigate possible extreme or not necessarily outliers, but impossible values. It happens. I work with different people all week long. Every day of the week, people bring me their data and they always say, okay, I've got my data cleaned. And almost 100% of the time, we find at least one variable that has scores in it that are wonky. It's like it's supposed to be gender. Male is 1, female is 2, 3 is other, 4 is refused to respond, and then somebody has a 37. And they're like, that shouldn't be there. But it just ends up that data, for whatever reason, even when you think it's clean, it always has some wonkiness. So that's why those are the 2 reasons I always say plot your data first. 1, to find those wonky out of place values, and 2, to understand what the distributions are one at a time. There's just no, I will tell a story. Here's a story that it will hopefully convince you. I was working on the memory study it's the dementia progression grant that I worked on for 12 years here for the Center for Epidemiologic Studies. And it's a huge study. It started with over 5,000 elderly people in Cache Valley. It's what I did my dissertation on. It's world-renowned study on Alzheimer's disease. But we were doing one analysis, and at the time I was still in the master's program. So my mentor, Chris Corcoran, who's been the department head of the math and stats department here, brilliant man, he ran one of the analysis. I prepped the data set and gave it to him. And I prepped it in SPSS, and he ran the analysis in another program called SAS. Programs are just tools, that's fine. But in SPSS, you can mark missing code. You can declare different values as missing codes. And in this study, we happened to, somebody refused to answer something, we marked it as a 998. And if it was just missing for just random reason, it was 999. And if they didn't know, it was like a 997. There were 3 different missing codes, 997, 998, and 999. Well, in SPSS, they were declared as missing. But when he pulled the data into SAS doesn't have the ability to mark those as missing codes. So I can't remember what the variable was. I think it was like a depression scale that usually went from 0 to 50. But if they were missing, then they had these 999s or 998s in there. He didn't plot the data. He didn't run descriptives first. He just ran a model. And so those 999s were treated as real values. And guess what happened to the model? It was so awful. And we were trying to figure out these results. We're like, the relationships that were showing up in these models were just not expected, and like the reverse that we expected. And we're like, why is this happening? And we finally went back to the drawing board, and it was, he didn't think to run the descriptives, and I thought I had cleaned the data because they were declared as missing in my program, but his program couldn't. So again, even if you think your data is clean, you'll want to plot it to check for those anomalies, because it delayed us several weeks in running the analysis, because we thought we were done, and then we were trying to write up the results, and it was so weird. And once we deleted those 999 type values, it like fell into place, and we were all good, and we went forward. But it was really frustrating for a while. So you want to get those out of there as soon as you can. Okay, so this was a great question, Kimberly. Thank you for bringing it up. Does anyone else have anything you want to talk about, either with these or anything else in these chapters?
I have a quick question.
Yeah, Laura.
So going through just the homework on 6B number 2 and on number 1.
Share your screen. I'll stop sharing this one.
Okay.
Here, let me stop. And that way everyone can see where we're at.
Okay. So you want me to share mine?
Yeah, go ahead and share yours,
Okay.
because I'm sure that somebody else has the same question.
Okay. So I got through, this portion just fine, but I'm trying to figure out what to do when we get to trying to find the two-tailed p-value.
Melissa's smiling because she was asking the same one at the start of class. I love that.
Oh, okay, good.
Question. So first off, let's make sure that, can you scroll up a little bit and let's make sure.
Yeah.
Okay, so this is 6B number 2.
Yeah.
6B number 2. Okay. All right. So you filled in your sample size, your average, your standard deviation, your hypotheses equal to 36 or greater than 36. So important to note, this is a one-tailed test. Very important. Unusual, right, but that's what it is. Okay. And so your standard error for the mean, you got 1.874. I got the same thing. Okay. And your t, you got 13 degrees of freedom. The t value is 3.36, the critical value. Now, based on the critical value, what do we know about our test? Our observed t-score is 3.3, but our critical value cutoff is 1.77.
That's what I'm trying to figure out. I'm not.
With just looking at those two, we can say that it's statistically significant, right? 3.3 is more extreme than 1.77.
Yeah.
We just need to know how extreme. Can you pull up the T table? I see you've got the book on the next tab. Perfect.
I might need to refresh it. Let me just see.
Oh yeah, sometimes. So it's statistical tables. Yeah.
Let me try refreshing.
Oh, it's gonna make you log in again. Yeah.
Yeah. Just a second.
Yeah. I'm so glad you asked about this, Laura, because you're not the only one. Is anyone else wanting to know about this? Hillary, are you saying yeah? Yeah.
Okay.
So reading this T table is different than the Z table. Yeah. So I think you can do your arrow over, or yeah, scroll down to get to the T table. I think one more. There it is. There she be. Okay. So it's important to note there's two tops of the table. There's the one-tail test and then the two-tail test. What kind are we doing?
This one test. But this has a two-tailed.
Does it say?
With the two-tailed p-value.
Oh, I did ask for the two-tailed p-value. Okay. I probably shouldn't have, but we'll go with it because that's what's down. Okay. So let's go with the two-tail.
Okay. So
can we change this so that the instructions match? Because at the top of the item, it says one tail, and then down there at the p-value, you should say two tail. Are you guys okay if we change that so it matches, it's consistent, and do it as a one tail?
Yeah.
Has anyone turned this in? Okay. We'll leave it then. We'll leave it as a two-tail because people have turned it in. I'll have to make myself a note to change that. I don't want to screw anyone up who's already turned it in.
That was part of my confusion, and that's why,
Yeah, that is very confusing.
why I kept getting it wrong.
Yeah, because the answer, I think, is probably marking it according to the one tail,
Okay.
which is why, you know what, let's do it as a one tail, and Kimberly and Melissa all auto grade yours. Because that'll be better. Okay, so let me go in and change this. Okay, so this is 6B number 2. Okay, so I'm going to change it. So where it says the two-tailed p-value is now going to say 1. Here, let me push save, and then if you refresh, it'll show on your screen. Let me push save first. Okay, now refresh yours. You do the swirly, yeah.
Oops. That's not what I want.
Okay.
On page 4. Yes. Yeah.
There, so now it says one tail. Okay, so that's consistent. So now that one is consistent with what's above it. Okay, so let's go back to I'll remind ourselves again, this is a t value with 28 degrees of freedom, and it's equal to 1.91.
Or 13 degrees of freedom.
Oh, I have the right, I wrote it down wrong. Okay, that's something else. 3.30 is our t value with 13 degrees of freedom.
Yes.
So to the t table.
So go to 13.
Yep. Can you highlight the 13 line?
Yes.
All the way across.
I guess I highlight the whole thing if I do that.
Oh my gosh. It's
But if I go across 13 over to.
So we go to the 13 line, and we're looking across the line that has 13 degrees of freedom, and we're trying to find our number 3.3. It's probably not going to be exactly there. So we're trying to find where would it be if it was on that line. So it would be
between these two.
It would be between the last two numbers in the table. So then you take those last two numbers and you go straight up to the top of the columns, and we're going to look at the two tail. So those two columns that it would be.
Or the one tail now.
Huh?
We're doing the one tail, right?
One tail. So yeah, so we go all the way up to the one tail test. So it would be between 0.005 and 0.0005.
Okay.
And that's what our p-value should be.
Okay.
We can't, with this table, we cannot get it down to 4 decimal places. With this t-table, we can just say between which values it would fall, unless it's like way off one end or the other.
So is the answer keyed as the one-tailed p-value or the two-tailed?
Yes, it is. So the one that you've just marked on there between the 0.0005 and the 0.005, that should be the correct answer. So if you click that.
Okay. Phew. Awesome.
Okay, and then Melissa and Kim, I will auto grade yours because the instructions were not consistent before.
I'll stop share.
It's a great question. Thanks, Laura.
Well, Sarah, I think I got mine wrong regardless, because I tried what I thought it would be and it wasn't right. So I tried 2 others. So I ended up on one that isn't going to be right regardless. So it doesn't matter.
Well, I'll auto grade it. Other homework questions, chapters 5, 6, 7, 8. Yeah, Melissa. Mute.
It's behind my second monitor.
Oh, okay.
I'm wondering if we could do 6A number 5.
6A number 5. Do you want to share your screen, please? So one sample test where we don't know the standard deviation of the whole population. our standard deviations coming from the sample. Okay. Oh, I think it's only, I think on recording, it's only recording. I need to do this. It's not letting me. Melissa, do you want to unmute your?
The 6A number 5
Okay.
is on item 2, I think.
Item 2, yeah. Okay, there we go.
There we go. There we go. Okay, so we have a sample size of 22 in which the average is 14.7 and the standard deviation is 6.2. Those sample statistics were given to us. The hypothesis is based on okay, so the hypothesis is that it's 6.5. This was a typo in the original assignment. Kimberly, I think you were the one that alerted me to this. So if you read the original direction, the top directions, the population mean is 6.5. The first time I typed it, I just put 6. I left off the 0.5. So on the hypothesis, Melissa, it should be 6.5.
Oh, okay.
And that's probably because you did it before I had fixed the typo. And I was just copying it out of the book and I just missed that. Okay,
For
so
some reason, I keep getting
so that's gonna
this.
yeah. So our t-value is going to be the average we observed, which is 6.2, minus the hypothesized average, which is 6.5.
Oh, okay.
So the average is 14.7. Sorry, I was reading the standard deviation. The average you observed was 14.7 minus the hypothesized average is 6.5 divided by your standard error,
Which is,
the 1.3218.
okay, that will fix this. Was there a similar problem like this on number 6A, number 6?
6A number 6.
Because I ended up with another problem with my T.
Okay, so let me see.
Maybe did we use the same information? Oh yeah, I used everything the same. So that's would be why I got this answer wrong.
Yeah, that's why that one would be wrong. Now, well,
Okay.
Yeah, because you use the same, no, your standard error for the mean is not the same.
Oh, it is for me. That's what I got for SEM.
6.6609. What did you have down on the next one, part B? Keep going down. Oh, that is right. That is right.
Okay.
I mean, that's.
Yeah. So it's just
The reason why this is wrong is because
6.5. Yeah.
that changed. Okay. That's why I couldn't get it right. Well, that fixes my problem then. I was like, I don't know what I'm doing wrong here.
I'm glad you brought that up because that's a change. That was a typo that I fixed because Pierre brought it to my attention. This is, yeah. So if you guys ever think there's a typo in the answer or the problem, please let me know. Other questions?
Thank you.
Kelly, let's see, Brian, Sam, are you guys all good? Leah?
A really random question. I still can't figure out when to put a 0 ahead of the decimal or not.
A really good question.
Okay.
The 0 in front of the decimal, you put a 0 in front of the decimal if that number in front of the decimal could be something that's not 0.
So like p-values should have the 0, right?
P-values never have the 0 because a p-value is always going to be point something.
Okay.
P-value is never going to be 3 point something. It's always going to be 0 point something. So the 0 is not needed.
Okay, thank you.
So far, things that we've learned that don't, a p-value does not need a 0 in front of the decimal. Are there any other numbers that we've learned so far? I think that's about the only one we've come across so far.
Okay.
Today, we're going to learn about correlation coefficient R, and R is always between 0 and 1, so that's positive or negative. So that's always going to be a point something in the real world. So R, the Pearson's correlation coefficient, does not get the 0 in front of the decimal.
Thank you.
Okay. But so far, p-values are the ones that don't.
Sarah, just one thing that tripped me up on the homework, just for others to be aware of. On that question that Melissa was looking at, 6A number 5 and number 6. So the second part, or part B of 6A number 5, changes the n value. And then on 6A number 6, it changes the s value, and I accidentally left the n value changed.
Oh, you have to go back to the original n value on 6A, yes.
Yeah. So
Yeah.
just throwing that out there in case anybody else gets stuck on that.
Good heads up. Good use of our time, I think. Okay.
We are having office hours tomorrow, is that right?
Yep, tomorrow at 7 o'clock, I will have office hours. I will be in my car at the swimming pool again on my phone, but you guys can share your screens with me, so that'll work. So 7 to 8 tomorrow evening. Yeah, definitely.
Thank you.
If you can't make it and you want to chat with me, we can set up a Zoom, even if it's just 10 minutes here or there if you need it. I know everyone's got different stuff going on in your life, especially more than ever right now. So just let me know what works for you, and we can find some time to chat if the office hours don't work for you. Or if you're stuck on something, I'd rather jump on for 10 minutes or 5 minutes and get your question addressed instead of having you wait 24 or 48 hours. Send me an email, say, hey, I'm stuck on this problem. Can you either answer it quickly, or is there a time we can jump on Zoom? I'd be more than happy to. Okay. Without further ado then, last call for questions. Okay, then let's go on to our slideshow. Today we're going to do chapters 9 and 10, correlation and regression, and they are a nice pair of topics. So I have, let's see, I need to share my screen. I'm going to share, let's see, I'll share the screen. Okay, I think that worked. Okay, so chapter 9, correlation. Okay, so far, I'm guessing not many of you have read the chapter yet. Is that a correct assumption? Not read it yet? Okay, so this is a first exposure, okay, at least in this course context. So this is why I love statistics. I love this quote, that statistics is not like a lot of other fields like physics, chemistry, biology, even education. I don't study statistics just for the soul of solving statistical problems. I study statistics to solve problems in all of your disciplines. And that's the great thing about statistics, is it's very useful in all disciplines. That also means that anyone who gets a PhD is also kind of minoring in statistics. So whether you knew it or not, you're more or less minoring in statistics, whether you want to or not. So here are some a motivating example for the topics we're going to start to cover here with correlation. So it goes something like this. Dr. Mortimer is interested in knowing whether people who have a positive view of themselves in one aspect of their life tend to have positive views of themselves in other aspects of their life. So he has 80 men complete a self-concept inventory that has 5 scales. 4 of the scales involve how competent the respondents feel in areas of intimate relationships, relationships with friends, common sense reasoning, and everyday knowledge, and academic reasoning, and scholarly knowledge. The 5th scale includes items on how confident the person feels in general. So we got these 4 sub-scores and then an overall score. 5 scores for each person. So he computes 10 correlations between all possible pairs of variables. So how these things are associated or connected to each other. So that's the difference with correlation. Correlation is saying how do variables or scores or domains, or how do they compare to each other? When we were doing the t-test, we were comparing groups. How do groups compare on the same score? Here we're looking at different scores where they're taken on the same person. We only have one group of people, but each person gets multiple scores, at least 2. Correlation is a pairwise measurement. It links 2 and only 2 variables together. We cannot do a triad correlation. We can only do 2 variables together at a time. So if you've measured 5 variables, we compare the first one with the second one, the first one with the third one, the first one with the fourth one, the first one with the 5th one, and on and on and on. And there's 10 possible pairs there. So correlation is trying to assess the degree of covariation or co-relationship among pairwise multiple variables that are on the same subjects, the same people. We're not interested with group differences per se, but if we have ordinal variables, we call it correlation. If we have nominal variables, we call it association or dependence. The variables depend on each other. So association is more of the general term. Correlation only applies if the both measurements we're looking at, both scales, are ordinal or continuous. So it would make sense to say, is someone's IQ correlated with the amount of money they make? Because IQ is on a continuous ordered scale, and dollars you earn in a year are on a continuous ordinal scale. So we would say, are those things correlated with each other? If I want to know, does ethnicity correlate with, I would not say, does ethnicity correlate with income? Because ethnicity is not an ordinal variable. There's no order involved with ethnicity. It's definitely a grouping variable, a qualitative or nominal variable, and we would want to know if there was some association. Do some ethnic groups make more or less than other ones? But we would use the term and phrase associated with or dependent upon. We would not use the word correlation if one of the variables does not have order in it.
I found this on the web.
Oh, thank you. Siri's looking things up for me. Okay, so the levels of measurement for each variable determine the type of correlation coefficient. So there are more than one type of correlation coefficient. We are only going to learn about Pearson's correlation coefficient. Pearson's correlation coefficient is when both of your variables are continuous. If they're ordinal but not continuous, we can use Spearman's correlation coefficient, but that's not really covered in this class. But we're going to do Pearson's is specifically for 2 continuous variables. If we have one continuous and one variable that has 2 levels, like yes or no graduated high school, yes or no is a parent, if we have, or male, female, there's 2, if we're going to score it that way, 2 levels. We have a 2-level variable with a continuous variable. We can use Pearson's correlation coefficients. And when we do that, it's referred to as the point by serial correlation. So that's just kind of a side note. A nice thing about correlation coefficients, Pearson's correlation coefficient, is that it can be done on raw data or standardized data. It does not matter. The units that you measure with do not matter. So we can record temperature in Celsius or temperature in Fahrenheit. It doesn't matter. The correlation would be the same if we did correlation with temperature and, I don't know, day of the week or something. This is really nice because a lot of the measurement scales that are used in social science don't have meaningful units. Like height, we can use inches or centimeters. Temperature, we've got Celsius and Fahrenheit. Depression, what are the units of depression? Reading ability, what are the units of reading ability? Intrinsic motivation, what are the units? I mean, depends on how you're measuring it, what the number's gonna be. The units are kind of irrelevant. I mean, they're just not having physical markers as much. And so Pearson correlation coefficients are very nice when you're using scales that do not have physical units to them. It's scale independent. So when we do hypothesis testing for correlation, we're going to have a null hypothesis. The null hypothesis is nothing going on. If we have two variables and we want to know, do they correlate? Are they associated? The null hypothesis is no, nothing's going on. There's no correlation. And no correlation is the score R equals 0. So in the population. So we don't, okay. Let's look at this plot first. This is one of my favorite slides in this whole course. Here we have a plot over 10 years, and for each year we have the number of movies that Nicolas Cage appeared in that year, and we also have the number of drownings in swimming pools for that year. What do you notice about those two scores? Shaking heads. What do you notice? Unmute that mic and
They
There's
follow a
similar
similar
lines.
pattern. Yeah.
there's definitely some pattern here. On years when Nicolas Cage had a lot of movies, there were a lot of drownings. On years like 2003 when he was, in 2008 when he was in less movies, there's less drowning. There is definitely a correlation or an association here. But is there a cause and effect relationship? Do drownings cause Nicolas Cage to be in more films? Or do Nicolas Cage films cause people to go drown themselves in a swimming pool?
Well, it might cause me to go drown myself having to watch him in all these films. I could be in this and be causation instead of correlation.
Correlation, yeah.
Not fair. He's a national treasure.
That was a good one. That was good. One of my favorite movies as a young teenager was City of Angels. Oh, Meg Ryan and yeah, so good. Okay, so Nicolas Cage. So we can make a similar plot and have like months of the year, and instead do drownings and ice cream sales. And there would probably, and this is the one I need to get a picture for, probably be a similar trend. When there's more ice cream sales, there's more drowning, and when there's less ice cream sales, there's less drowning. Not cause and effect. Why in that case, the ice cream sales and drowning, why might we see an association there?
There's a third variable of maybe temperature. It's hot.
There is a third confounding factor that is responsible for or driving the association we see. Just because two variables are associated with each other, just because they're correlated, does not mean one is causing the other. It could be that they're both being affected by a third outside variable. And that third outside variable
Well,
that,
in the Nicolas Cage one, it's going to be that if I have to watch all those movies.
maybe his movies came out in years that were like really hot and swinging, high economy, everyone's out playing years, I don't know. I don't know what the third factor that's responsible for it. Sometimes we can never pin it down, and we call this a spurious result. Sometimes if you look at enough variables just by random chance, you're gonna find a pair that look like there's an association. But if you were to do it again, you wouldn't, a different sample, you wouldn't see it. You can't rule out just random chance for seeing some pattern. I think this one was just people hunted around till they found a funny one. Tyson's the one who found this one. But there are lots of times when we can see things are being associated and we get really excited, but you have to rein yourself in from making your conclusion be worded as a cause and effect. Association does not imply causation. Now here's the rest of the sentence. In an observational study. If you are observing, here we're observing the years, we didn't randomly assign the number of films Nicolas Cage got to do. We didn't randomly assign drownings. We didn't affect anything. We just observed what was naturally happening. So we cannot draw a cause and effect conclusion. The only time you can draw a cause and effect conclusion is if you have randomized your groups or your exposure or your independent variable and then followed up and measured your dependent variable. Here we don't really have an independent and dependent variable. We're just looking at two variables. So that's very important, and I cannot state that strong enough. So much our research questions are based on the hypothesis that there's a cause and effect relationship, but if we can only gather observational data or maybe semi-quasi experimental, we have to be really careful about how we write our conclusions and not use this causal relationship language. And it's so hard because you want to, but you have to acknowledge the limitation of an observational study. So I've said it before, I'm saying it again, we always want to visualize our data. So when we're going to do the simplest situation where we just have two variables. You have two variables, we've talked about how to plot them one at a time. If you are then looking at the relationship between two variables, you want to plot them two at a time after you've plotted them one at a time. And the way you plot, the simplest way to plot variables two at a time is called a scatter plot. So scatter plot, you put one variable on your x-axis and the other variable on your y-axis, and then each person's pair of scores, you go over and up and make a point. The next person, you go over and up and make a point. So each dot here is an observation or a person in our data set. In this plot, there's a lot of points. And then here I've overlaid the regression line, which we'll talk about more in the next chapter. But you can see that there's this kind of trend where points, observations that are higher on the x-axis, more to the right, are higher on the y-axis. They're up. So people are either high on both or they're low on both. We see this kind of relationship. This is called a positive correlation. And if you have multiple groups, which sometimes we do, you could make one of these for men, one of these for women, one of these for, you know, whatever groups you have. But generally, this is the best way to kind of get a glance at our relationship. So over here in the bottom corner of the slide, I have the code for making a scatter plot. So let's look at this and compare it to the other plots we've made. We start with the name of our data set and pipe it to link it to the next step. We good so far? Then we're going to go into Ggplot Aesthetics. Now in the aesthetics, we now have to not just give one, but we have to give two variables. And if you only put their variable names, the first one will be the x-axis, the second one will be the y-axis. But you can also say x equals the variable name you want on the x-axis, and y equals the variable name you want on the y-axis. We'll see another example of this. So the aesthetics, you tell it which two variables you want for the x-axis and the y-axis. And then we plus to add a layer into our plot, not a pipe, I know. But now we're going to use geom point. Geom point will add those dots onto your plot. And that makes the scatter plot. That if I just stopped with geom point, I would just get my dots. Now this regression line on there is really handy to put. And in R, how you add it is geom smooth. It smooths out the pattern of the points. Now, there's some options in the parentheses for this geom smooth. By default, it does what's called a low-S smoother. We want to make a linear model or a linear regression line, and that's why we have to say method equals LM, and that makes the linear regression line. If you had left off method equals LM, it would make a moving window low-S smoother, and it wouldn't be a straight line. It would be kind of a wobbly line, depending on your data. The SE equals false part of this is usually by default, it puts confidence bands around your regression line and it shades them. Sometimes we like that, sometimes we don't. This turns it off. I'll show you another one in a second that has them on. Okay, so the scatter plot. Here are two different pictures of two different scatter plots. On the left, with the green line, this is where we say it's a positive relationship. So reading from left to right, the line is going up. Positive slope from our algebra class. Positive association. It means high values on one variable are paired with high values on the other variable. Upper corner, low on one variable, low with the other, lower left-hand corner. The blue line on the right side has a negative association. Negative means high is paired with low or low is paired with high. It's the opposite. Can anyone think of two variables that would have a positive association and another pair of variables that would have a negative association? I want everyone to come up with a pair of variables that you might be studying, that you measure on the same person, and everyone take a turn and say a pair of variables and whether you think that they would be positive or negatively associated.
Just tell you or say it?
Yeah, just
So like, what about time studying and overall GPA?
Yeah, time study, a student spends studying and their overall GPA. Do you think that's positive or negative association?
I'd hope positive.
You would hope positive. More time spent studying, higher GPA, less time spent studying, lower GPA. Think that's reasonable.
So mine is smoking and stamina with a negative association.
So the more someone smokes, the less stamina they have. Yeah. Yep.
I put down as a negative association, stress levels and spouse arguments.
Stress level.
So the more stress would be like, oh, no. More stress would be more arguments. That'd be positive.
Maybe stress and marital satisfaction.
Yes.
More stress with less satisfaction would be a negative relationship.
Yeah. Sorry, that's what I was going for.
Yeah.
Age and reading comprehension. As people get older, their reading comprehension goes up.
So would that be positive or negative?
Positive.
Positive. Yep.
Oh, sorry.
I'm so sorry. I was going to do professional development time and teachers' classroom quality scores would be a positive association.
More professional development, more better classroom, higher scores. Yep.
I wonder if that was true. How interesting. Sorry.
Oh, okay. Level of engagement and degree completion.
Yeah, more
That'd be
engaged.
a positive.
Complete.
Yeah.
Positive. Sam,
Education.
Oh, I just said I wonder if that's a true correlation, professional development and classroom scores.
It's not really. I oversimplified.
Yeah. Kimberly, did you have one?
I'm
said-
wondering about homework
go ahead,
completion and test score.
You would hope homework completion and test score would be positive. You'd expect it.
Positive.
Yeah. Kimberly?
Income and education level.
More education, more income, less education, less income. We all bank on that, right?
That's what we bank on, yeah.
Brian, did we get yours? Yeah, okay, awesome. So direction is positive or negative, and that positive or negative is the sign that's on the Pearson correlation coefficient, a positive number or a negative number. Then the actual number of itself denotes the strength of the relationship. If you have no relationship, the correlation is 0. If you have a perfect relationship, it's correlation of perfect +1 or perfect -1. So here we got two pictures. On the left, that correlation is a perfect +1. On the right, what would you think that correlation would be? Positive or negative?
It's still positive.
Positive.
It's not very strong.
It's not a perfect 1.0. That's for sure. This is why on correlation, if you look at that perfect 1.0, how often does that happen in real data?
Never.
Never, never. There's always some noise or some random fluctuation. That's why correlation coefficient, we don't put the 0 in front of the decimal, because it's never going to be 1. It's always going to be point something or negative point something. So this correlation might be 0.8 or 0.76. It's going to be a positive number, but it's not going to be a perfect 1. But it's going to be closer to 1 than it is to 0, probably. It's hard to eyeball the actual number. We can do the sign, positive and negative, eyeball it pretty good, but the actual number, our eyes don't, they trick us sometimes. So here are 4 more plots. The upper left-hand corner, this is a linear relationship, and I want you to compare it to the one underneath it. What shape do you see in the lower left-hand corner?
The U.
The U-shaped. Is it a straight line? No. So this is very important to note. Correlation only measures linear correlation. Now, what kind of positive or negative would be this top plot?
Positive.
Positive relationship. Now, in this bottom one, is it positive or is it negative?
Neither. It's like
It
0.
starts out negative, and then it's plateaus, and then it goes positive. So correlation is not a good thing to do unless you have a straight line pattern in your data. If you have a curved pattern, correlation, linear correlation is not a good measurement to use. It's not that it's not correlated. I mean, there's definitely a clear pattern in that bottom left-hand plot. It's just not a line. And so it's really, I want to stress that Pearson's correlation coefficient only is applicable or only meaningful measurement for data that exhibit a straight line. And if you plot your data, always plot your data first, and you see this U-shaped up or down or a hook or kind of a plateau, that's fine. That can be totally right on, really strong, but correlation coefficient is not going to capture the strength accurately. Now, if we look over at the right hand, the top and bottom plot, both of those plots are no relationship. Now, the top right hand one, if you kind of squint your eyes and you try to tell, could you tell if it's a sloped up or sloped down, positive or negative? Can you tell for sure? It's almost impossible to decide if it's going up or down. That's no relationship. That is correlation of 0. The bottom one can be tricky. It's a perfect straight line, but it's a perfect flat line. This is a correlation also of 0. And the reason is, when variables are correlated, that tells you, if you know the value of one variable, it gives you information about the other variable. If I know someone is high on age, I know they're probably higher on reading ability. If I know someone has a higher education level, they're probably going to be in a higher income level. In this bottom right-hand plot, if I know where someone is on the x-axis, does that help me know where they are on the y-axis? No, everyone's the same here. This one happens less often, but sometimes we're using measurement scales, and when we actually collect the data, there is almost no variation in our sample. If you have a variable with no variation or very, very little variation, you cannot extract any information. And so that's why I threw this one up on here, because sometimes we won't see it perfectly flat, but we'll see almost completely flat. Okay. So when we have correlation, it's indicative of having predictability. If we have the ability to predict one variable from the other. Okay, here I have, just ignore the writing on here. I just want you to look at the points. I have 4 different scatter plots. Which one has the strongest association, the strongest correlation, do you think?
Bottom left.
Bottom left? Everyone agree? Someone have a different idea? Laura goes with you. Kelly? Leah? Yeah? Anyone else think something? Does anyone think one of the plots is more strongly correlated than the bottom left?
So it looks like the top right has a sharper incline, right?
Has a sharper incline, most definitely, but it is a stronger correlation. I want you to read the text at the bottom of on the bottom of the slide. All
Oh, no, yeah.
are the exact same data.
The X and Y.
The X and Y axis have been stretched and condensed.
Interesting.
What happens to the picture when you stretch or condense the X and Y axis?
It can look great or bad.
You can change the look a lot. This is how some people try to lie with stats or data or plots. This is not a good thing to do. Which one do you think is the best representation of this data?
Bottom left, because it says
Bottom
good.
left is the one that says good. There's a hint, right?
I think it's really funny that you told us to ignore the text, and I totally didn't read the bottom. It said all the same data.
Good
I'm
job.
an English teacher. I should have known better.
My old slideshow gave the plots without the text before, but this slide has it all together. But yeah, so the bottom left, the one that says good, that is the way that Ggplot will plot this if you don't tell it differently. Ggplot in R is really, really good at choosing your axis spans. It will span your data, but not beyond. If you look at the upper left-hand corner one, what do we notice? All the points are in the middle, and what about most of our real estate on our plot? It's mostly wasted. When you have a lot of wasted space, you can make your data look very, very different. It's not a good idea to do. So we won't have to look at that. Okay, I want to look at this outlier idea, but I want to do it back up here. I want to go to this app first. So I went a couple slides down to get this app. This app is one of my favorites. It came with a textbook I used to teach Stat 2000, I think, a long, long time ago. This is a close version of it anyway. Okay, so this is nice because we can play with correlation without a lot of numbers going on. So here I have 2 points I've made. 2 points, it tells us, and the correlation coefficient is perfectly 1.0 because I can make a perfect line through those points. Now I'm going to put a third point. Okay, there's my correlation. Lovely, lovely. What do you think is going to happen if can you guys see my mouse moving? Okay, what happens if I'm going to put another point in the upper right-hand corner? What do you think is going to happen with the correlation coefficient? Do you think it's going to get closer to 1 or closer to 0?
Closer to 0.
Let's see. What is it right now? Take a look at it now. Watch the correlation coefficient. Right now it's 0.79. I'm going to add another point. Oh, it got closer to 1. What if I add another point in this bottom left-hand corner?
Closer to
1 or closer to 0? Okay, well, let's watch it. It goes from 0.86, 0.89. When I add points that fit the pattern, our correlation gets stronger. Correlation, you can think of it as how close the points fit the regression line. So here's our line of best fit, our regression line. Okay, I'm going to clear it out. Okay, so here I'm going to put some points down here. So what kind of correlation is this? This is a fairly strong positive correlation, okay? So if I put, how much now do you think adding an upper right-hand point will change the correlation? Do you think it'll make it get a little stronger or a lot stronger? Think in your mind what you think this correlation of 0.75 is going to change to. You got a number in your head? Let's see how it changes. Whoa, did you think it would change that much? It changed a lot. Now, what would happen, do you think, if I put the extra point in the upper left-hand corner? Okay, think of what you think this number is going to change to. Right now, it's 0.75. You ready? Did it change a lot or a little? A lot. What if I put it down in this lower corner? Now check out the correlation. I made it a negative correlation by adding 1 point. Okay, let me make an arch pattern. What's the correlation? Is it positive or negative? It's pretty close to 0. Yeah. And if I add 1 other point, I can make it negative or I can make it positive. We've seen this kind of thing happen before. What other thing did we see value or calculations change value with 1 extreme value? What else is susceptible to extreme values?
Is it the mean acceptable to extreme
The mean is susceptible to extreme values. The standard deviation is susceptible or changed by an extreme value. So is correlation, and then also right along with it, regression. All of these things can be very much influenced by extreme values. That's why it's so important to plot your data. Now, if we plotted our data and it looked like this, should we just throw this one out automatically? No, but we might want to go back to our notes and our files and say, number 1, is this an allowable value? And number 2, was there something different going on with this person that maybe makes them unreasonable to be included? Okay. So outliers can influence correlation a great deal. All right, so we've seen with the mean, if we calculate the mean based on a sample, what symbol do we use for the sample? The mean is?
X bar?
X bar. And for the population, what do we use for the mean?
Mu.
Mu. For the standard deviation, for the sample, we use S. For the population, we use sigma. So we have this pattern of using typical regular alphabet letters for the sample and Greek letters for the whole population. We're going to continue that. For Pearson's correlation coefficient, and sometimes it's called Pearson's product moment correlation coefficient, if it's based on just data from the sample, we use the letter R. But if it's based on the whole population, which we usually don't know it, but we're hypothesizing, we use this new Greek symbol. This symbol is called rho, R-H-O. It's like a P, but it's curls on the top. It's just one curl. So we've already said that it ranges from -1 to +1. It's influenced, can be influenced by extreme points, has both direction and strength. Okay, here's the formula. Lovely formula. Good news, we don't have to memorize this formula. I'm never going to have you use this formula by hand. But let's break it down a little bit, okay? Let's look inside these first set of parentheses. What do we have here? We have xi, that's of a value. And what are we doing? We're subtracting x bar, the average, and dividing by the standard deviation. Let's think back. What do we call it when we take our number, we subtract the average and divide by the standard deviation?
Standardizing.
Standardizing. That's
score.
Some of the
yeah. So here we're making the x values z-scores. And then in the second parentheses, we're making the y value into z-scores. So that's the standardizing. That gets rid of the units. It puts them in number of standard deviations. And then what does it mean when you have two things just sitting next to each other in algebra? They're just sitting next to each other. What's the math we do? Multiply. So we are multiplying the z-score of the x values and the z-score of the y scores. So that's why it's the product moment. The product comes from the multiplying the two z-scores. And then what does the sigma thing mean? Add it all up. So for each person, we're going to make their z-score of their x value, z-score of their y score, y value, and we're going to multiply them together. For each person, we're going to add it all up and divide by n minus 1. That's degrees of freedom. Is that making it unbiased. So yeah, who wants to do this by hand? No, we're going to let R do this for us, okay? Because really, if this is just a million chances to make a little arithmetic error. Okay, so here is a plot of data on the left-hand side, X and Y. And then on the right-hand side is the same data, but I've made them z-scores. I've standardized X and standardized Y. What do you notice about the plots, other than the axes? The plots are identical. So when we make z-scores, remember we said before, when you make a z-score, you change the center to 0, you change the spread to 1, but when you make a z-score, you standardize, but you don't change the shape. So if we standardize the x scores and standardize the y scores to make them z-scores, we don't change the shape at all. We just get rid of the units. So here's the R code to do it not by hand, okay? So there's two different pieces of R code I'm going to show you here. This is the first one. You take the name of your data set, you pipe it in to an old function called core.test. We're going to test the correlation, core.test. Now we put a tilde wave. Now when we did our t-test, we put our continuous dependent variable before the tilde and our grouping independent variable after the tilde wave. With correlation, if you do the correlation between age and reading level, and then you switch the order and you do it between reading level and age, you get the same thing. The order doesn't matter. So for correlation, when we do the formula, both of your variable names, both of them come after the tilde wave, and we connect them with a plus symbol. So if my variables are called x and y, I do nothing in front of the tilde wave, but both of the variables added together on the right side of the tilde wave. And then we have to give the data that's typing from above a place to land by saying data equals dot. And I believe the default method is Pearson's, but you can specify, because this core.test function can do Pearson's correlation, Spearman's correlation, and I think there was at least one more it can do. So we are only doing Pearson in this class. So that's the code that you will use on the homework. You'll just change the name of the data set and change the names of the variables. And this over here on the right side is the output it gives you. It tells you that you did a Pearson's product moment correlation. The actual correlation is the bottom number. What is the correlation between these two numbers? How would we report it in APA? Would we start with the 0 or would we start with the decimal? We'd start with the decimal and let's report 2 digits. We'd say 0.05. Or if we were going to do 3 decimal places because we were fancy, we'd say 0.054. Okay, so that's the correlation is at the bottom. That's our point estimate for correlation. It also gives us a confidence interval around that point estimate. Our best guess at the correlation is 0.05, but we're 95% sure the correlation is between negative 0.14 and positive 0.24. That's a pretty big range, and that range is going from the negative zone to the positive zone. Negative or positive, that's not very clear. It could be negative, it could be positive, we're not really sure. And if we look at our p-value, our p-value is not significant. Now with our null hypothesis, The alternative hypothesis is that it's not equal, and it cut it off, it says 0. The null hypothesis is that it is equal to 0. No connection, no correlation means correlation is 0. Is our correlation exactly 0? No, but 0 is a plausible value because it's inside this range. Now, the other code you can use to do correlation is in Tyson's furniture package. We've used table F and table 1. There's also table C. C stands for correlation. The nice thing about table C is you can give it 3, 5, 10 variables, and it will make a correlation table of all of those. So here I'm using the same 2 variables, X and Y, very generic. So here is, let's look at the numbers that it put in this table. Well, the first number I've highlighted is 0.054. What is that? If we look at our full core.test output.
That's your T, is it? Or is that?
That's the actual correlation in the.
Okay, it just matches T. Oh, not quite.
The T, this isn't, the T will be very, very close to, well, it's 0.53, but it's a version. There's a connection between the T and the R. But yeah, this number that's in table C is the correlation in the sample. So we'd use the letter R because that's the sample's correlation R. What number is in the parentheses here? Can you find that on the output? 0.594.
The p-value?
That's the p-value. So when you use table C, it just reports the correlation R and its p-value. But if you do core.test, it gives you a whole bunch of output. Sometimes we want all of it, sometimes we just want the simplified table. Core.test is, I find, more useful if you're only doing 2 variables. This table C is very nice if you have a whole bunch of variables, like 3 or 4 or 5 or 10. Okay, so we already talked about linear relationships versus nonlinear. We did the correlation app. Okay. Now we said with assumptions, there's assumptions for every statistical model. I have this up in my office. All models are wrong, but some models are useful. And the usefulness depends on how well we meet the assumptions. So these are the assumptions for testing correlation. We have a random sample. Have we heard that assumption before? Yeah. How well do we usually meet that? Yeah. How can you test that? How can we test having a random sample? Anyone have any ideas? How can you run a test to see if your sample's random? Sam?
It's just the test we talked about at the beginning of class, right?
It's not one of those. This is a trick question. There is no test for randomness. It's a trick question. I wasn't trying to trick you on purpose, but I was trying to make you like rack your brain.
Yeah, Dr. Schwartz.
There is no test for random. All you can do is plan the best that you can with the situation you're dealing with. Number 2 assumption, that your relationship is linear. Well, what does linear mean? A straight line. How can you tell if it's a straight line? You make a scatter plot and you squint your eyes and you say, does it look about straightish or does it look really not straightish? The third assumption is that you have a bivariate normal distribution. Bi means 2, variate means variable, so you have 2 variables, and it's that not just that they're normally distributed by themselves, but their connection between them makes a bivariate normal distribution. And that's what this 3D plot over here is trying to show. So we know what a normal distribution is, a bell curve. That's in one dimension. So it's like you actually have a bell if you did the 3D plot. Now, this last little bullet under here, this is less important as your sample size gets bigger. And if you have a small sample size, this is almost impossible to assess. So usually what we do is just look at the variables one at a time and see if they're normally distributed. How do we tell if a variable is normally distributed? This is not a trick question. There is an answer to this one.
Shapiro Wilkes.
Shapiro Wilkes that we talked about at the first of class is one of the ways.
Is this if like it significantly changes the correlation? Would that make it?
We want to know if each variable by itself makes a normal curve.
So we could also make plots.
Yeah, we can make the histogram or the QQ plot for each variable, or we could do Shapiro Wilkes test. Okay. So when we are doing a test of correlation, our null hypothesis is nothing is going on in the whole population. So the correlation in the whole population is 0. So when we write our null hypothesis, we don't use the little letter r, we use the Greek letter rho because it's for the whole population. So our null hypothesis is in the whole population, there's no association. And usually we do a two-sided test with the not equal sign. So Kimberly pointed out the t value. The t value is, this is the formula for it. I'm not going to have you do this by hand, so I just wanted to point it out that you use the r, and r is involved in this formula, and capital N. And the capital N in this means, what do you guess? What do you think N means?
Population.
It actually means the sample size.
Mm-hmm. Oh.
Sample size. Now, at the bottom of here, this slide has the degrees of freedom. This degrees of freedom is for correlation. When we did a one sample t-test, the sample size was, or the degrees of freedom were n-1. When we did a two sample independent sample t-test, it was the combined sample -2. For correlation, the degrees of freedom is n-2, not 1. And there is a table in your back of your book that you can use. We're not going to use this table in the back of the book. We're going to use our output. We're going to ask R to do this for us. So here's a little data set, and it has 7 people in it, and it has, for each person, we have a score for their mood, like positive or negative mood. And these scores are in the 20s, 30s, and 40s. And we have how many words they recalled on a test. This is a verbal recall test. It's in the 20s, 30s, and 40s. So here I did I started with the name of my data set. I piped it into core.test. First thing I give it is the formula, which is tilde wave, and then the 2 variable names added together. And I said data equals dot, so that the data can flow from above. Here is my output. What is the correlation in this sample?
6.4.
0.643 or 644, we'd round up. What is the correlation in the whole population likely to be?
Close. Close.
What? Close? Close to?
Isn't the whole population going to be close to the sample as long as you have normally distributed?
Random sample. Yeah, but look at our p-value. What does our p-value say? We can't fail to reject. We can't reject the correlation. What's the null hypothesis? Nothing going on. The correlation is 0. Check out our confidence interval. Negative to positive. It could be either. So even though the correlation in this sample is 0.644, we have no evidence that there's any connection in the whole population. Because, and here's one thing, how big is our sample size? TD? TD? So notice that how big is our sample? N equals 7. What's our degrees of freedom? N minus 2. So 5. Okay. Okay, we're not going to do this power stuff. Things that affect variability. This is important. So we've already talked about outliers. We said extreme values can heavily influence correlation. So this is why we plot our data. That can be very influential. Range restriction can also be very influential of correlation. Now, I find this is especially an issue for educational research. So a lot of times, educators or people that are doing research in the classroom use classroom assessments. So summative assessments, like at the end of a chapter assessment. I want you to think about a class and like a test, end of chapter test and end of class test. What are the scores like? There's a range, usually between 0, let's do it as a percentage, 0 and 100%. Where are the bulk of the scores probably going to be?
On the right.
70, yeah.
If you're a teacher and you're doing your job, you're hoping that they're all going to be clumped at the upper end. So if here's 100%, is it going to be a normal distribution?
No.
No, because people are going to max out at 100%. This is a big problem with correlation because correlation assumes that the distribution is normal. And so if it's not, you can have problems. Let's see, I can't draw on here unless, let's see, do this right here. So, come on, here it comes. Oh, clear all. Clear all. Okay, so if this was our test, 0 to, let's do 0 to 100% is our test. And maybe this is hours studying. There's a maximum number of hours that students can study, right? Because there's a number in the day and they have to be at school. And so there's like some maximum and there's a maximum on the test. So what you'll often see, so there is just this restricted range. You'll see a lot of students like up here. And if this is most of your students, your correlation might not be very strong because everyone who would have been up here, there are some kids that would have studied more if they'd been given more of a chance. And if you'd had a harder test, they would have scored higher. And you're like cutting it off just because of the way it is. And so you get a lot of, if we were to look at this histogram, it would look like this. If we were to look at this histogram, it would look like that. So your correlation, even though it might be really strong, might only come out to be 0.7 instead of what you might expect to be 0.9. And it's because of the just virtue of having a restricted range, because correlation does best if you have this almost football shaped distribution. That's what a bivariate normal distribution tends to look like, is more of a football, not a cut off football. So what can you do about this?
Don't use end of chapter tests.
End of chapter tests can be problematic. These just regular classroom assessments, they're nice because they're already being given, but you really have to think about if you are doing your research for your dissertation or any other purpose in a classroom, those end of chapter, end of unit, naturally occurring assessments might not be appropriate for research. You might have to give a different test or have extra questions on the test that can get your students on the upper end not all maxing out, but kind of spread them out. So there are other kinds of tests that you can give that give more room on the upper end or the lower end. Usually it's the upper end a lot with these summative assessments that have the problems. So this is one of those things that during the planning stages you need to think about. The other thing here is a heterogeneity of samples. So if I was looking at correlation between age and height of middle schoolers, is there a correlation between age and height in middle schoolers? Is it positive or negative? Positive. Older kids are taller, younger kids are shorter. But are there subsamples within that group where the correlation might be different? Can someone chime in, Laura?
Well, just with like puberty, I think it would throw things off. There might be some really tall 6th graders and some really short 8th graders, you know.
If you've ever spent any time in a middle school or with that age of kids, there's drastic changes that happen. And I was thinking in my mind, what about the girls and boys? The girls usually hit puberty before the boys, and the correlation might be different between the boys and the girls. And if you just lump them all into one sample, you might have the girls doing this and the boys doing that. But if you lump them together, you're going to weaken your relationship. That's an example of a heterogeneous subsamples of having boys and girls lumped in the same sample. So sometimes it would be better to do correlation among girls and correlation among boys instead of just correlation altogether. Depending on what you're studying, it's not always the best to lump your sample all together. Sometimes we want to separate it out and do correlation within subgroups. And we've already talked about correlation is not causation. Can't make that jump unless you're in an observational study. Okay, at the very bottom of this slide is the APA format. So the APA format for correlation looks a lot like the APA format for a t-test. We put the letter R. Now this is one thing I've seen differently, even though people all say they do APA. The parentheses after the R are often left off altogether. But if they are given, they're supposed to be the degrees of freedom. And the degrees of freedom should be, what's the formula for degrees of freedom for correlation?
N minus 2.
N minus 2. I have also seen it published where people actually put the sample size without subtracting 2 there, and they'll actually write N equals 100 in those parentheses. APA says it should be the degrees of freedom though, but usually the sample size is given elsewhere in the manuscript, and so people often will leave that off altogether. Sorry for the bad news that nobody's consistent with that. But the correlation comes first, R equals whatever number it is. Now with correlation, do we need a 0 in front of the decimal? No. If it's positive, you don't need to put a positive sign, but if it's negative, put the negative sign. And then after that, you put a comma and then the p-value to 3 decimal places, unless the p-value is tiny. If the p-value is tiny, what do you type? P is less than 0.001. Okay. So here's a couple of slides about APA reporting. So this top one is, let's see, let's look at the R. Okay, first, right off the bat, they say there's 9 students. Now this came out of an APA manual. I copied it out of it. And it's interesting because the sample size is 9, there's 9 students, but look at the very last thing in that sentence. What's in the parentheses after R?
8.
What should it be?
7.
7. Whoever made this manual, I don't know. It should be 7. Okay. So notice they're giving some background. They say there's 9 students. They are giving here we've got the first quiz and a first exam, and they're giving the means and standard deviations for both of those in the parentheses. And then they're saying that they are strongly and significantly correlated. Strongly because it's 0.7 is closer to 1 than 0. Significant because the p-value is less than alpha 0.05. So that's an example of one sentence with correlation.
Strongly because why again?
It's closer to 1 than 0. Now, you're never going to see correlations of 0.98. It just doesn't happen, usually. A correlation of 0.7 is actually strong. Now, there is not very great cutoffs for strong, weak, medium, and strong. Generally, 0.5 is moderate, 0.78 is strongish, 0.23 would be weak-ish if you wanted to have some kind of like cutoffs to think of. So kind of Cohen's cutoffs for Cohen's D, 0.2, 0.5, 0.78-ish. Though you can think kind of on those. Again, it's fuzzy about where the cutoffs are between weak, moderate, and strong.
Sarah?
Yeah.
So for APA reporting, do we need to make sure and put like the mean and standard deviation of the first exam in that order, or mostly just concern ourselves with the R and the p-value?
Yeah, it depends on if that is the focal point and that's like the be-all end-all of the research. Usually a correlation is kind of a sub-aim or a sub-point in the analysis, and so you would already have the means and standard deviations in a table 1 or another table somewhere else.
Okay.
Yeah, so in this purple lower box that it's written out, it says a Pearson product moment correlation coefficient was computed. So it's telling us what they did. The test that they ran was computed to assess the relationship between the amount of water that one consumes and the ration of skin elasticity. So those are they are telling us that they did a correlation between these two variables. You've got to say what you did a correlation, and these were the variables you correlated. There was a positive correlation between the two variables, R, and in parentheses it says 5. So what would we assume the sample size is? 7. And it's, oh, notice this correlation. Now, what did they do wrong on this correlation?
They put a 0.
The 0 in front of the decimal. Now, 2 decimal or 3 decimal places, you know, as long as you're consistent, I'm okay either way. Check out the p-value.
There's a 0.
There's a 0 in front of the decimal. Ah! And they say a scatter plot summarizes the results in figure 1. Including a scatter plot is a very good way, if that's like the focus of your research, to show the relationship. Overall, there was a strong positive correlation between water consumption and skin elasticity. And then they say what the meaning is in terms of these things. Increases in water consumption were correlated, not caused, but correlated with increase in rating of skin elasticity. Notice they didn't say drinking more water causes skin to be more elastic, because it probably wasn't a randomized study. You would only be able to say it caused if you randomly assigned people to drink certain amounts of water. So there's a table here. This is an example of a correlation table. So in this example, they have multiple variables: age, probably of the study, age of onset, duration, positive symptoms, negative symptoms, disorganization symptoms, and then PFAI and VBR, which down in the bottom it says what those are. But so we have a lot of variables. So there's a lot of different correlations. Now, a correlation table like this, you notice there's only numbers like in a bottom triangle. That's because if we filled out the top half, it would be a mirror image. Now, right in the first variable is age. If we go over from age with age is left blank because every variable is perfectly correlated with itself. So we usually leave the ones on the diagonal off of a correlation table because it just clutters it up. So the correlation between age of the study and age of the onset of whatever it is they're talking about, that correlation is 0.82. Now, they did not need to put the zeros in front of the decimals, but you know, whatever, it's still the same. So 0.82 is pretty strong. And then next to the 0.82, there's 2 asterisks. What do the 2 asterisks tell us?
Double significant.
It's double significance. I give them a naughty mark on this. They say an asterisk is the level of significance p less than Oh, 1, but it doesn't tell us what's the difference between 1 asterisk and 2 asterisks. They should say. They do say something about a Bonferroni correction. We're going to learn about that in a few chapters. And notice also at the title, the table has a title at the top. It should say table 3, and then on the next line, it should say correlation coefficients with each word capitalized. They didn't do that right either. But notice that these are Spearman correlations, not Pearson correlations. Just point out. Okay. So this is the cancer data set we've seen before, just to go over a little bit more syntax before we call it a day on correlation, and then we'll take a break. Whew. So here is the cancer data set, and I'm piping it into core.test, and I am correlating the total condition at intake. Remember, this is their oral canker condition in their mouth at intake and at 2 weeks. Now, by default, it does method equals Pearson, but you can write that out. By default, it does a 2-sided, and that's what this comes out. So is there any, yes or no? I want everyone to vote yes or no. Is there evidence of correlation between the oral condition at intake and 2 weeks later? Is there evidence of a correlation? Yes, there's evidence, or no, there's not? Laura, up or down? Brian? Down? Hillary? No? Okay, the correlation is positive 0.31. Isn't there a correlation?
So it's a weak correlation, but it's there, right?
It's
Well,
there.
and the p-value is not significant, so.
The p-value.
Hmm.
The p-value is non-significant. What do we notice about our confidence interval? Negative, positive, both are feasible. We're not sure which one it is. So we would say there's no evidence of a correlation. At least this sample provides no evidence that there's a correlation. Can we absolutely say that they are not at all correlated? No, we just say that there's no evidence of a significant correlation. In the sample, there is a weak correlation, but there is no evidence that this holds true in the greater population. Okay, so notice the confidence interval. What's the default confidence interval? 95%. Okay, and by default, it does a 2-sided alternative. Again, these last 2 lines, alternative equals 2-sided and method equals Pearson, you don't have to write those. Those are the defaults, but you can change them if you want. Notice on this second one, I said alternative equals less. Less than what? What's the null hypothesis? Correlation is 0. So what would be less than 0? Negative correlation. So this is how you would change it to a 1-sided correlation, testing if they're one-sided alternative hypothesis, testing if there is a negative correlation, is you add in alternative equals less. And if you wanted to test if it was a positive correlation, that means correlation, it would be bigger than 0. So you say alternative equals greater. So that's an option you can change in the core.test command if you want to go instead of a 2-sided to a 1-sided hypothesis test. So here's an example of doing a correlation table with 4 variables. Instead of having to do all the different core.tests, you can do them all together. Now, when I did this one, notice what happens here on this bottom line. What am I seeing in this correlation table? NAs. What did NAs stand for?
It's not data.
There's no data. Correlations can only be computed if you have complete data. In this data set, everyone has their condition at intake, 2 weeks and 4 weeks, but there were some people that left the study before the 6th week. So by default, table C will do what's called listwise deletion, or pairwise deletion. It does pairwise deletion. Anyone who's incomplete, no, it doesn't do, it tries to do everyone. So if any variable that has missing values, it's going to put NAs. So the NAs down here on this bottom row are evidence, or they're showing you that this last variable has missing values in it. So by default, that's what table C does. If a variable has missing values, like this week 6 one, you get these NAs showing up in the table. Now, if you want to go ahead and calculate the correlations, throwing those incomplete people out so you can get something, then you say na.rm equals true. That stood for NA is missing, RM is removed. So it says missing people, remove them. And then you get this table down here. Notice on the last line, now we get values. Now look at this first number up here that I'm highlighting, the 3.14. That's the correlation between week 2, because that's the line it's on, and then right above it is this square 1. That goes with intake. So this correlation of 0.341 that is non-significant, so the non-significant correlation that's between week 2 and intake is 0.314. But check it out down here in this next table. It's different. It's not 3.14 anymore. That's because this table only includes people that have complete data on every variable that we're using. So anyone who is missing the 6th week is not included here. It's doing list-wise deletion. If anyone is missing any of the variables in this list, they're thrown out of all of the correlations. Now, the other option is pairwise deletion, where you only delete it for the pairwise correlation. The problem with doing that is then all the correlations in the table have a different sample size on which they're based. So that's why Tyson chose to do listwise deletion for the option here. So this na.rm equals true does listwise deletion. It deletes from the analysis, the whole table, anyone who's missing any of the variables in the table.
So like if there's a missing variable in, say, the intake, and they take that out, is that because they all belong to the same person, say?
That
so
person comes out of everything.
That whole person's gone.
The whole person's gone.
Right, okay.
Any person with partial missing data is removed completely from all of the correlations. So if this data set originally had, I don't remember how many people, oh, we can look here. Degrees of freedom are 23. What was the sample size then? 25. So this table would have all 20, this is for all 25 people. This correlation would only be for the, I think there's 21 people that have complete data at all 4 time points.
So on the first table, are they just does it throw out the person? If
no one gets thrown out, but if there is a variable that has missing values, it does the NA.
Oh, okay. But like if they only say they had a missing value for intake only,
then this intake correlation, all these correlations that involve the intake variable would be NAs.
Would be NA, but it's not like they'll throw it out completely like on the next one. Just for the variable. Okay. Sorry, that was really confusing me. I apologize.
No, that's fine. The way that different functions or commands deal with missing data is not trivial. And different functions and commands deal with missing data in different ways, and they will affect your analysis and your results depending on how they handle missing data. It's something you need to look into anytime you learn a new function or a new command. What are the defaults? What can I change? And what in the heck does it do with missing values? Because I guaranteed you're gonna have missing values in your own data. It's very, very rare that we get complete data. I mean, wouldn't that be nice? Okay, so here's another example of code to do the scatter plot. So again, with the scatter plot, you say the name of the data set, get my cursor over here, name of the data set, pipe it into Ggplot, then in the aesthetics, you give it the 2 variables that you want to plot. If you just put the 2 names, the first one will be the x-axis at the bottom, the second one will be the y-axis. So you control the order to control which one's x and which one's y. And then the geom point puts the points on. Here's if I do geom smooth with method equals LM, that does the regression line. And notice it does these shaded bands. This is the standard error band for the regression line, which we'll talk more about in the regression chapter next. But you can get rid of those bands by adding the option after method equals LM or before that somewhere is capital SE equals false. And that's what we did on, where is it? Get back here. Where did we do it? Here. See, we added the SE, oh, it's lowercase SE equals false. That makes it not draw those bands on, the standard error bands. Okay, we're almost done. I need a break.
I mean, they don't hurt anything if you have them there. You could leave them on as.
Sometimes they're just clutter, and sometimes we just don't want the clutter on there. It's personal choice. Okay, so this is geom point. Geom point puts a point for each person. Now, sometimes this is oral condition. What do you notice about oral condition? It can be 4, 5, 6, 7, 8, 9, and then someone is 12. They're whole numbers. There could be what's called overplotting. People that have the same scores and they would land on top of each other. There's no way to tell with this scatter plot if there are multiple people like stacked up, their points stacked right on top of each other. There's no way to know. So I'm so happy that Ggplot added a new command. So instead of doing geom point, we do everything the same, change it to geom count. And what this does is it makes the point bigger if more points had landed there. So it's like if it was you can think of them as drops. So if 2 raindrops hit the same spot, it would expand out. So now we can see that, and we get this little key, that there are 3 people here, and 3 people here, and 3 people there, but only in 2 and 2, and then these other ones are 1. So the size of the dot, this is really helpful if your measurement scale has more discreteness to it, and there's not a lot of fine-grained continuousness to your scale. But that's just another option on your scatter plot, is instead of just doing points that might stack up together, you can do counts to make them bigger or smaller depending on how many. Okay, we need a break because next we're going to do regression. Okay, anyone want to, let's see, it's 3:30 now. Let's go to 3:40. Well, 3:38. It's only take 10 minutes, and then we'll should be able to cover regression in our last 45 minutes. Okay. I'm going to take a little walk. I shall be back. I probably should have paused the recording. Oh well, too late now.
Sarah, so on the homework for 9, we won't have to use any of those formulas to do stuff by hand. We can just use R.
Yeah, let me double check and make that. I was just looking at that and making sure. Yeah, that's describe things. Yeah, I have the data sets. So they're in some of these sections they have toy data sets, but yeah, you use R to do the correlations. Yeah.
We'll just put their data sets into R and run it from
Yeah, they're already typed into the skeleton.
Oh, great. Great.
Yeah, you won't have to type in any of these little data sets. I already have them typed in.
Okay, so since there's nothing to do that's not in R, then there's no sense doing the homework by hand on the sheets.
The sheets have, well, yeah. There's some of it on the sheets, like the first couple questions say, they're write out questions. They're not math questions. I think I'm going to change them to matching, where you drag and drop so that they auto grade. And then there's multiple choice question. Section A, and then in section B and C, yeah, it's all with R. But the R skeleton file is there. In fact, I'll link it right now so that when you open it up, you can find it.
Oh, well, if the R skeleton file's there, then I can just go look at the paper one and do the homework.
Yeah, let me go here. Let me link it right now while I'm thinking about it. I'll do it for 9 and 10.
Thank you. I've got my grandkids are coming for a staycation this weekend, so I took tomorrow off work, so I'm just gonna sit and do all of this.
Aw, it's so fun.
It will be fun.
We miss Grandma. My mother-in-law lives a block and a half away, but they're susceptible, so we've been keeping more distance than usual, and it's rough.
My grandkids, their other grandma is like that. So, but my daughter has 4 little ones, and she's like, they're driving me crazy being at home with 4 little ones. So they come over all the time, and it's a lot of fun. But now they get to spend the weekend overnight.
Yeah, my sister has been going crazy, and so I actually have 2 of our kids at our house. So I have 6 kids now, because more the merrier.
That's a lot of kids.
Yeah, well, they're all fairly self-sufficient. They're not young. I've got a 15-year-old, a 13-year-old, and then my 12-year-old nephew and my 14-year-old niece, and then 10-year-old and an 8-year-old. My 8-year-old is the most mature out of all of them.
No, those are good ages. My grandkids are between 2 and 9.
Yeah, those are a little bit more attention.
Tons of fun though, but yeah, my dad's like, I've got to get out of the house. They're driving me crazy.
Let's see, there's the linear regression. I just
Sarah,
was the first person in the building all semester. Yes.
so I just wanted to ask about APA formatting, like on test questions, like which part you're looking for.
Okay, so this is a really good question. So on the homework, there are things like that, right?
Mm-hmm.
So let me open up. Oh, I have to go into atomic assessment. So part 7, that's the piece of this, right? So this is last question I think on homework 7.
We can't hear you. It's
you still can't hear me.
sometimes it just comes and goes. I'm not sure if there's.
And you can't hear me now.
Oh, now I can.
I didn't change anything.
Yeah, I don't know.
If I cut out, let me know and I'll figure out something.
Okay.
This is on homework 7, the very last one. It says report your results as they might appear in a journal article. And then it has these directions here, including this little table about what are methods and what are results.
Mm-hmm.
This exact thing I have pasted into the exam on the question. Okay. There's 2 questions that I ask you to do. Report your results as you would in APA.
Okay.
So I grade them the same way. Now on this one, let's see, let me open up the answer key so I can see what it is. So this one was a correlation, right? Oh no, do the 2-sample t-test to determine whether coffee drinkers exhibit significantly higher post-quiz heart rates than non-drinkers at that 0.05 level. So if you were going to do this one, let me see, I think I can do preview. There, now I can do it. So if this was me, I would want to start, just check off these bullets. First, I want to set up the situation to describe the participants' variables in the experiment. So you could say, a sample of 100 students in a stats class took self-reported whether or not they drank coffee, and if I can spell right, and then took their heart rate after a pop quiz. So I've said who my students are, who's in my sample, and what are the things that we're measuring. Okay. Self-reported whether they drink coffee and their after the quiz heart rate, right? So I got the 2 variables, okay? So that's setting up the situation. Now you could put in lots of averages and lots of summary information, but that's good enough. Now, usually in a journal article, you're gonna have like a couple pages about your methods and a couple pages about your results. And your methods is gonna go into more about your recruitment strategy, and you're gonna go in about, it's gonna have a lot more details. Here, we're doing like very abbreviated, like 1 sentence for each of these bullet points, or maybe a sentence for combining the bullet points are sufficient, okay? So setting it up, and then what are the assumptions and how are they tested? Oh, so we're doing a 2-sample t-test. What are the assumptions? It's a good thing to talk about. What are the assumptions of a 2-sample t-test, independent groups t-test?
Aren't they similar to the assumptions for the z-test?
They're very similar.
Okay.
Anyone come up with one of them?
They're normally distributed.
Normally distributed. What's normally distributed in this case?
The means.
There's only one mean, or there's two means, a mean for coffee drinkers and mean of non-coffee drinkers. But can we talk about normality of means? What would we talk about normality with regards to?
Distribution.
Distribution of what? Normality is a distribution, but of what?
Sample.
Of what?
The sample.
What about the sample? What about the sample should be normally distributed?
Mean.
The mean is one number for coffee drinkers and one number for non-coffee drinkers.
The heart.
Heart rate.
The heart rates. So heart rates were plotted, and the histograms plural for both coffee drinkers and non-drinkers were approximately normally distributed. I'm like going bonus points here. Did we actually do that? No. What else can we do to decide if it's normally distributed besides making histograms? We talked about it at the very beginning of class today.
Shapiro Wilkes test.
We could also do a Shapiro Wilkes test. Okay. So normally distributed, the continuous variable that we're comparing the two groups on, that should be normally distributed. That's one of the assumptions. There's two more assumptions. It's going to be on your test.
They were randomly sampled.
Is it that we have a random sample? It should be that we have two independent random samples. Now, do we know that here? No, but we're going to treat it that way. Because how can we test if the sample is random and independent? We have two random samples that are independent of each other. How can we test that? Trick question, we can't test it. We just have to plan well and sample as best we can. So assumptions, number one, that we have two independently gathered random samples. Or the other exception is if we have one random sample that we then divide on based on a question they answer, like, do you drink
All
coffee?
the ones we have are so long for us all.
What was that?
I think someone's cutting into like our frequency or something, because it's like we're getting interference.
Ah, that is weird. There's like no one in this building. Saw one person today. That was weird. Okay, well, let's keep going on. So we've got the assumption that we have simple random sample, that the participants in the two groups are independent of each other. We can't really test that. Normality, we can do Shapiro Wilkes or make a histogram. And then there's a third assumption.
It doesn't have anything to do with the spread, does it? The spread?
Yeah.
Okay. That the spread of the sample is the same as the spread of the population?
That's the one sample assumption. But in the two sample, what do we just have to assume with two samples and spreads?
They're about approximate. They're similar.
Yeah, what's that called? What, Hillary?
Homogeny of variance.
Yes, I knew I saw your mouth make the words. Homogeny of variance. Homogeny of variance means that the two samples have approximately the same spread. And how do we test that?
Levine.
Levine's test. Levine's, and in this one, you actually did Levine's test in the R code. Levine's test found no violations to the assumption of homogen. Can I spell this right? I never can spell this right. Homogeneity of variance. And what do we report on homogeny of variance? What numbers do we need to put in letters and all that jazz? Here it is. That's an F value that has 2 degrees of freedom that are stacked up on the output. You guys see this? This is tiny. Let's make this bigger. So we say, what's our sample? What did we measure on them? Assumptions we have here, we have the normally distributed and homogeny of variance. Those are our assumptions. Now, where did I get these numbers? I got them out of the R Levine's test that I have printed out right here. It didn't come from this guy. So we've set up the situation. We described the participants and the variables or anything that we did to them. We had the assumptions and we told which ones we tested and how. Now what's the main test we're going to run? And independent groups t-test for mean difference was conducted to see if coffee drinkers had higher heart rates than non-drinkers. That's the test we're going to run, right? What's the dependent variable? The dependent variable is that continuous variable measurement we're comparing. What are we comparing the two groups on? We're comparing them on their
Heart rate.
Heart rate. And then the independent variable is the grouping variable. That's whether or not.
Drink or non-drink.
So that's this part. So did we get all 3 bullet points for the methods? Yeah, we have who we have, what we measured on them, what were the assumptions, and what's the test we're going to do. That's the methods section. Then, so this is basically a methods paragraph or collection of a couple sentences. Now we need to do the results. We need to describe the trend we see in the data. So I don't have it here, but if we had the averages, we could put in the means and standard deviations. We don't have them here, so I'm not going to worry about them. Now we need to put the results. So as long as they're in here somewhere, the order doesn't make a huge difference to me, but now we need the conclusion. Conclusion, including direction, confidence intervals, if it's significant. So if we come up here, does anyone have this in front of them? What this last one? I'm pulling it up on mine. This one had 98 degrees of freedom, and it was negative 3.19 was the t-score. The p-value was 0.002, and the 99% confidence interval was negative 5.344, just 2 decimal places, to negative 0.51. Okay, so what is this telling us? What's our conclusion?
Statistically significant.
Statistically significant what? It is statistically significant, but what's significant?
Can you go back up to?
The difference in heart rate between coffee drinkers and non-coffee drinkers is significant.
Yeah, so there is evidence that coffee drinkers and non-drinkers have different heart rates, but we need to say the direction, which we don't have the averages here, but it's the coffee drinkers that have the higher heart rates. We'd need the descriptives to see that. But now, why is this negative? Are all of these things negative?
Because of the way we subtracted in the
It's
beginning.
order of the subtraction. So here we've got, let's see, can I open up the R code so we can see the R code, what it outputs? That will be helpful. So let's see. We come to the answer key for the assignment. So this is 7, right? 7. Okay. Run this all. Okay, so see, here's the Levine's test. What does this Levine's test tell us about homogeny of variance?
It's not violated, it's fine.
It's not violated, the assumption is fine, as far as we can tell. Okay, so here's where I did the t-test, comparing heart rate post-quiz based on whether or not they drink coffee. So here it gives us the descriptives down here. Regular coffee drinkers, their heart rate is 71.57. Maybe I should put that in my thing. That would be a good thing to include, right? Coffee drink, non-drinkers, the heart rate was mean equals 71 point, what was it, 68 beats per minute. And what is it for coffee drinkers? 74, what's 57? Decimal place, 71.57 and 74.5. Coffee drinkers. Beats per minute. And this is, I got that wrong. Do you have to include the standard deviations? Not necessarily. The key here is we're doing an independence group t-test for the mean difference. And we see that coffee drinkers have a higher average than the non-coffee drinkers, but now we want to know, is it statistically significant? And how do we tell? We look at our p-value. Is our p-value significant? Yes, it is. Laura said statistically significant. What's statistically significant?
The difference.
The difference in
Heart rate.
Heart rate. So if there is a difference, we need to say direction.
So the heart rate of coffee drinkers is significantly greater than the heart rate of non-drinkers.
This is evidence that coffee drinkers do, in fact, have, now we can apply it to all coffee drinkers in the population, have higher heart rates than non-drinkers. And this is where we put our test statistic, T98, Now, whether or not you make it negative or positive, usually we are, don't. And then we need to put our confidence interval. Yeah, 99% CI. And it was what? You can put it from, as far as most of the time people don't care if you put them both negative or both positives. If you're going to drop your negative signs here, we would usually put the smaller number first. So we would reverse the order. So this is the kind of thing that I'm looking for on the APA conclusion. You need to say, at the very least, you need to say you did an independent groups t-test for mean difference, and you need to be making it clear you're comparing coffee drinkers and non-coffee drinkers on their post-quiz heart rate. You've got to say something about your assumptions testing, and then you need to include what your conclusion is. In this case, there was a significant effect, so you need to say in which direction. So here, the coffee drinkers have higher heart rates. Every person in the class, every semester I teach this could have it written differently and it could still be correct. Anyone have any questions about what they should include or not include, or how they could alternatives to writing this up? Because this is a big deal. This will be on the test, almost word for word like this. Twice, actually. Know your assumptions. Know how to write your conclusions, for sure. The formula sheet will be on the test. The T-table will be on the test if you need it. I don't even think you do, but it's there. Can we calculate a Cohen's d for this? No?
Don't we need the standard deviation? We'd have to find that.
We'd have to find that. Let's go ahead and do this. Like when I taught high school, I told my students, if I stomp my foot, that's the indication that this is something you need to know for the test. I'm stomping my foot right now. Cohen's d. How do we compute Cohen's d by hand? Generally, what's Cohen's d? What's Cohen's d?
Sample minus population mean, right?
G power?
We use Cohen's d in G power. Anyone remember the formula for Cohen's d?
It's the x bar minus the x bar 1 minus x bar 2 over the pool
Variance.
the standard deviation, which should be the same, I think, for both groups. If it's not, it's more complicated than that.
Yeah. Okay, so this is really G, but we're going to do Cohen's d this way. It's the two sample averages minus, and we then divide by the pooled standard deviation. Here's the formula. Is that teeny tiny on your screens? I'm sorry. So here I've done table 1's furniture. So here are my two averages, 71.57 and 74.5. We've already seen those. So to do Cohen's d, what goes on the top? The 71.57 and subtract the 74.5. That would go on the top. What goes on the bottom? We need the pooled standard deviation. Did you know that you can use R just like a calculator? 71.57 minus 74.5. So there's the top of our Cohen's d. Now for the bottom, we need the formula for pooled standard deviation. So are these sample sizes the same? This one's 58, this one's 42. They're not exactly. For simplicity, we're going to pretend like they're the same. If they were exactly the same, we would just have to average our standard deviations. So let's pretend like because they're close. So how would we average our standard deviations? Add them up. Oh, come on. Add them up. 4.32 plus 4.82 and divide by 2. So how will we do Cohen's d? Let me get my formula back here. Come on, formula. You know, we subtract our averages to go on top. Our pooled standard deviation goes on the bottom. So I could go negative 2.93. It's so quiet when you guys aren't in the same room with me. The one on the homework will have sample sizes that are exactly the same. This one, they weren't 58 and 42. They weren't perfectly equal, but they were close.
So there's a sample or an example of this on the homework and the test.
Yeah, if it's on the homework and we talked about it in class and I'm telling you it's on the exam, it's probably going to be on the exam. Yeah. So Cohen's d, that's mostly what we did in the power chapter, because the power chapter 8, you need G power to do most of the power calculations, but you can do Cohen's d without G power, right? We could do, if you had this table, you could do this with just a regular old cheap $5 calculator, right?
And will this formula be given to us, or do we need to remember
Is
this?
that formula on the formula sheet? On the formula sheet, so you will have it. So here I'm going to go, here's our formula sheet off of our website. So on the test, this front side of the formula sheet will be all there, copied and paste. And then this top part here, and actually on the homework or on the exam, I called it G, because if you are using X bars and S, that should be called G, not Cohen's d. Cohen's d is supposed to be with mu and sigma, which we almost never know. When you're using the sample statistics, we should be calling it G.
Okay. So I didn't see this on the first test. It was on there?
Nope, this is on, because this is from chapter 8, so it would be on this exam, not the last one. Yeah.
So to get just one more time, to get the pooled standard deviation, I take the standard deviation of each of the samples, add them together. You're basically taking an average of the two.
So here is, well, and I kind of simplified it. This is the formula really for the pooled. You're supposed to square them, add them up, and then do the square root, but I kind of was lazy. This only works if this formula down here only works if the sample sizes are the same. If the sample sizes are not the same, you're supposed to do this 1 minus the sample size times its variance plus 1 minus the other sample size times its variance and divide by the combined sample size minus 2. This is a weighted average. If the sample sizes are the same, you can just do the standard average. It should be done with the variances, not with the standard errors, but I've been lazy. Let's do it the real way we're supposed to do it, shall we? So I'm going to square that. In R, you square it with the up caret. And then we should have to do the square root of that. It changed it just a little bit in the decimals. Here's our formula. It says the pooled standard deviation is equal to the fraction, where on the top you do S1 squared minus S2 squared and divide it by 2. Oh, I did that as a chunk. Where's that form? Oh, and that's SP squared. And then where do you get these S's, these S squareds? You have to take the standard deviations and square them to be in here.
So, Sarah, just a question, because the formula says SP squared.
Mm-hmm. That's why I had to do the square root.
Okay.
Because this, when I do this one, this right here, the 4.3 squared plus 4.8 squared over 2, that gives me SP squared, and I need just SP not squared in this formula. So that's why I had to square root it.
Oh, okay. Okay.
So I'd take this number and do the square root of that number.
Got it. Okay.
So when so this came out to be 0.64. So the way we would put that, I mean, it's not required here, but you would put, usually we either put a confidence interval or a Cohen's d or G. We usually don't put both. So I noticed that on the discussion boards, you guys loved the idea of a confidence interval. Some of you guys were like, why aren't we doing this more? And I said, I wish we would. But using a Cohen's d or G measure is trying to do the same thing of giving, or giving a standard error, giving an idea of how our accuracy or our precision of our measurement. But I prefer to give more numbers than less, and so I like to give all of them, the confidence interval and the Cohen's d or G, when I'm actually writing real manuscripts. Are we supposed to be done at 4:15? Yeah, we didn't get regression done at all. Which, you know, sometimes that happens. Let me see. I think the schedule, I want to say that we only have one chapter to do next, because we don't have class on Monday, right? Woohoo! Let's double check the syllabus. I'm thinking that we only have one section. Yeah, Wednesday of next week, there's only matched t-tests on the like lecture-ish calendar. So for regression, I will record a lecture on regression and you guys can watch it, and then we'll take the first 45 minutes of next Wednesday, a week from today, to go over regression. But if you've read the chapter and watched the video by then we should be able to do that fairly quickly. A lot of it will be very similar to the correlation chapter. There's a lot of similar main ideas there. Some difference, but a lot of connection between those two chapters. We good with that? Okay, so I won't meet you for class for a week, but there will be office hours tomorrow from 7 to 8. If you guys need and want me to pop on and Zoom one-on-one, or if there's multiple of you, that's fine either way. And then next week on Tuesday, I'll have office hours. from 7 to 8. And then Wednesday we'll have class. Wednesday we'll, like I say, try to watch the recording if you can at all fit it in the next week. And definitely get the chapter read and chapters 9, 10, and 11 and get those discussion points done after you get the exam and these homeworks done. And keep them in order. But are you guys feeling kind of worn out yet? We're halfway through. You are halfway through with this class. Can you believe it? Half of semester. You're doing awesome. You really are. Really, really good. Any other questions? I'm not going to start anything new.
I have a question. You probably answered this on Monday. Sorry, I wasn't here. About formatting the hypothesis for the homework.
On the homeworks, yes.
Yeah.
Let's look at some of those. Okay. So which chapter do you want to start with? Is there one, Sam, that you want to look at?
I know there are bunches in 5, but.
Okay, let's look at 5. Okay. Okay. Yeah, here's some. Go into preview mode. Okay, so on this one, her class has 36, so that's the sample average, or 36 students, sorry, that's N. And the mean of the class is 540. And we're supposed to say the general population has a mean of 500 with a standard deviation of 100. So that's for the general population. When we do our hypotheses, you've got to click in the box and use the menu system. So then what's our null hypothesis?
That they're the same.
Well, here we only have one sample in this one. So it's that the mean mu is still 500. Even though her class was 540, it's that the mu is still 500.
Okay, so you just put mu equals 500.
And to get the mu, where it says basic, if you click on there, you get 2 other little menus down here. The alpha one gives you all the Greek letters. So if you click on, when you click in this box, it'll bring up the basic thing. You have to click down on the word basic and go to the Greek letters to get mu, and then equals 500. On the alternative, its mu is not equal to. So you have to go to the menu that has the little alligator, the less than symbol, and that gives you, I didn't click on it there, that gives you the not equal symbol.
Okay. Thank you. Sorry.
Yeah, no, that's important to know how to enter those into the assignment. That's very important to ask. Now for the p-value. The p-value, you put 3 decimal places, but sometimes it happens as the p-value, sometimes it says 1.222 e to the negative 6. What does that mean if you see a number like that?
That the 2's go on for a long time?
Well, I learned the hard way. It means that p is less than 0.001.
When you see that little e in the number, that's scientific notation representation. That means times 10 to the negative 6. And calculators use it a lot of times, and so R uses it a lot of times too. It's the shortcut way of writing a really tiny number. So what this means is we need to move the decimal over 6 places to make this a smaller number. The negative tells us that, the negative 6. So if we move that decimal over 6 places, it would be 0.00000 and then the 1222. So this is a really tiny number. When you see this e to a -5, -10, it's a really, really tiny number. And the directions, oh, it doesn't show it here. At the top of yours, it says in the directions, if you have a tiny p-value, you type
less than 0.001.
Now that's not the answer on this one, but just you will come across at least one time on one of the homeworks that you, now it is kind of awkward because it says p is equal to less than 0.001. That's really awkward, but I don't know of a better way to do it on the homework. Okay, so if your p-value was going to be in 3 decimals, was going to show all zeros, you do less than 0.001. Good question, Sam. Okay, we're out of time. Does anyone else want to ask a question before you log off? Wow, we're ending on time. This is unusual.
I do have some questions, just going over the R assignment, but I can do that now, or we can.
We can do it now.
Okay. If anyone
And
else.
then when she's finished, I sent you an email because I don't know what I'm doing wrong, but I sent you a screenshot. So after this.
Okay, let
Thanks.
me stop the recording right now. And then I will restart recording, okay? Because I want to have this recorded, but I don't want it to be on this. It gets past an hour and it gets hard to, okay. Bye, everyone who has